So with this question here, we would essentially like to use L'Hopital's rule, but the idea is that we have to actually prove that we can. And the idea is that L'Hopital's rule can only be used for indeterminate forms such as infinity times infinity or 0 over 0. And we would essentially like to prove that we can use it on this type of quotient. But the first thing is that, it's not a quotient, right? It's not one thing divided by another. So we have to essentially equivalently express it as though it was a fraction of some sort. And there are really two ways you can do this if you wanted to express this as a fraction. The first thing is you can say that, like, if you have a times b, that's essentially the same thing as b over 1 over a, right? So this would actually come about to being it would come about to being the limit as x approaches infinity of sine of 1 over x divided by 1 over x to the 3 halves. Or you could say that, x to the 3 halves is equal to 1 over x to the negative 3 halves. You could say that as well. So sort of piggybacking on that idea, you could say that this is the same thing as taking the limit as x approaches infinity of 1 over x to the negative 3 halves times sine of 1 over x, which is the same thing as saying directly that this is sine of 1 over x divided by x to the negative 3 halves. And you can proceed from any one of these starting points. And essentially what you'd have to do in both cases is you'd have to prove that it's an indeterminate form. So in this case, it's an indeterminate form because if you do if you do a direct substitution, you'd have 1 over infinity over this, which would also be infinity. And so you'd have sine of 1 over infinity, which is 0. So you'd have sine of 0, and that comes about to being 0. So it's an indeterminate form. And the same thing could be said here. The same idea is said here. You'd have 0 on the top, and you'd have 1 over infinity. So I actually should have said 0 here. So you'd have 0 on the top, and then you'd have 1 over infinity, which is 0 on the bottom. So you'd have 0 over 0. So in both cases, you'd have to use L'Hopital's rule. So we can start from here if we want. We could also start from this version, but I guess we'll choose this path here. So the idea is, you take the derivative of the top and you take the derivative of the bottom, and then you take the limit of that and see if that gets you anywhere. So the limit as x approaches infinity. So we take the derivative of the top. So the derivative of so we're essentially doing d over dx of sine of 1 over x. So that's just cosine of 1 over x times the derivative of 1 over x. So the derivative of 1 over x. So we know that 1 over x is the same thing as x to the negative first. So we can actually say this is the same thing as saying cosine of 1 over x times the derivative of x to the negative first, which is the same thing as saying the cosine of 1 over x times negative x negative 2. And that is our derivative for the top portion here. And then for the bottom portion, we'll digress here and we'll say that the bottom portion would just be negative 3 over 2 times x. And then we would have to decrement the power by 1. So we would do negative 3 over 2 minus 1, which is the same thing as saying negative 3 over 2 minus 2 over 2, which would just be negative 5 over 2. So this is negative 5 over 2. So basically, I mean, these are our derivatives here. These are our derivatives. So we can put that back over here in terms of the limit. So we'll put the derivative at the top. We'll say this is cosine of 1 over x multiplied by minus x to the negative 2. And then this is in the bottom, we have negative 3 over 2 times x to the negative 5 over 2. And at this point, it's a matter of judging whether or not we'll still get an indeterminate form. And it's not apparent right now, but if you simplify this down, maybe it can be apparent. The first thing that you know, so if I were to simplify this in an arbitrary manner, I would probably say that negative x to the negative 2 is the same thing. So this on the top, we would have negative cosine 1 over x, because that negative would essentially preserve itself on the top. And then I could have negative 3 over 2x to the negative 5 over 2. And since I'm bringing this x to the negative 2 to the bottom, I'm going to flip the exponent and say that this is x to the 2, or x squared. And the immediate thing that I noticed there is that these sort of cancel out. So I don't have to necessarily worry about the negatives. And maybe I will bring the 3/2 to the top by multiplying by 2 over 3. So I'll multiply by 2 over 3. This would cancel out with this. This would cancel out with this. So I'm really left with the limit as x approaches infinity of 2 over 3 cosine of 1 over x divided by, so I'm multiplying both of these guys. And if you remember, like x to the a times x to the b is x to the a plus b. So I'll go ahead and add these exponents. I'll do 2 plus, or we can say 2 minus 5 over 2. You could have also said 2 plus minus 5 over 2, but that would just come about to being 2 minus 5 over 2, which is 2, 4 minus 5, multiplied these, cross multiplied these. We have negative 1 over 2. So in the bottom, it's x to the negative 1/2, which, I mean, if you brought this to the top, you would have the limit as x approaches infinity of 2 over 3 cosine of 1 over x times x to the 1/2, which we know this part here would just become under root x. And so you can then think about whether or not substituting infinity will give you an indeterminate form. So what we notice, we're not necessarily substituting infinity, but sort of substituting increasingly large numbers. And what we notice is we would have 2 over 3 cosine of 1 over infinity times under root infinity. So we would have 2 over 3 cosine of 1 over infinity would just be cosine of 0, which is 1, right? Because 1 over infinity is 0. And then times under root infinity. So you have 2 over 3 times under root infinity, which is equal to infinity.